webinar focuses on the Ground Source Heat Pumps Renewable Energy Center of Expertise. We are a remote group of experts from across USACE who focus on geothermal wellfield design and ground source heat pump design. Our mission is to enhance the knowledge base of the theory and practical application of ground source heat pumps throughout the Army Corps of Engineers. We function to support the project development teams from concept generation all the way through to the installation phase of ground source heat pump. We also aid in troubleshooting, design and installation deficiencies. We have a wide range of services that include project reviews of AE and in-house designs of geothermal well fields as well as ground source heat pumps. We also focus on ground source heat pump HVAC design, on well field design, on surface water heating as long as it has a ground source component to it. We're also available to answer technical questions from the field. We conduct webinars such as this one. We're also available for cost estimating, ground source heat pump, energy modeling, life cycle cost analysis, as long as it focuses on ground source heat pumps. And we've got a couple of parametric studies of different wellfield design configurations. We also offer consultation on drilling in contaminated areas, dealing with state regulators, how to identify substandard grout, and troubleshooting common subsurface well construction problems. We have a group of 22 team members who are experts in their field. They vary from mechanical engineering, geology, geotechnical engineers, cost engineering, electrical engineering, program and project management. And these experts are located throughout the Army Corps of Engineers. Although we are headquartered in LRD, our members come from most all districts. So if there's ever a project in a particular district, then we can always pull from our team. Our team members have a lot of different certifications. Many of them are registered professional engineers, registered geologists, certified energy managers, ICSPA certified geo-exchange designers, and LEED accredited professionals. We actually have another team member who anticipates on becoming an ICSPA certified geo-exchange designer, and another teammate who is going through the LEED accredited professional process. We have created a Sharepoint site, the link of which you will see at the very bottom of the presentation. On the Sharepoint site, there are links to best practices, design tools such as Trace 700, GLD, which is ground loop design, the Carrier Hat program. There's also a link for laws and standards, training opportunities. There are more than 9 training opportunities on this site, several of which offer PDHs, and they also offer ICSPA certifications for ground loop design. You will also find a section focusing on research. On the very first page of the Sharepoint site, you will find articles and case studies, a discussion board, and a listing of our services, which we've previously mentioned. We have a variety of projects going on right now. We have a couple of in-house project reviews currently going on and an upcoming AE review. We are in the construction phase of the Fort Campbell Sustainment Brigade Admin Building. And we are in the design phase of the Joint Base McGuire Dix Lakehurst Consolidated Dining Facility. A lot of us here are calling it the Fort Dix DFAC. Also in the works is a webinar to focus on ground source heat pump systems 101. This webinar would focus on the practical application of ground source heat pumps, when ground source heat pumps are applicable, and how to design a geothermal well field. There's also a parametric study of the different grout types to determine which one is better for different well fields, and a parametric study of SDR9 versus SDR11 tubing. And we are actually collecting in situ borehole test results for each of the different installations, such as Fort Dix and Fort Campbell. If anyone happens to have a geothermal test well report and they would like to share that with the group, please either contact me or feel free to add it to our Sharepoint site. This is one of the projects that we have just mentioned. It is the Fort Campbell Sustainment Brigade Administration Building. This is it's an energy pilot project, and it is under construction. It is almost 31,000 square feet. It is what we would call a full geothermal project, meaning that the geothermal well field is sized for 100% of the building load. So there's no redundancy with a boiler or a cooling tower. There are 69 boreholes, each with a depth of 415 feet. Each borehole is designed to be spaced at 20 feet from one center to the other. The airside system consists of variable speed air handler with VAV boxes. Hot water and chilled water are produced by water-to-water heat pumps. On the source side of the water-to-water heat pump is water that comes from the geothermal well field. The load side of the water-to-water heat pump comes from the building loop, which goes out to the VAV air handler and the VAV boxes with hot water reheat. This project is anticipated to receive LEED Gold certification. 36.97% energy cost reduction from ASHRAE 90.1 2007 baseline has been achieved. It has been approved through GBCI, which is the certifying branch of the USGBC for LEED certification. We anticipate 49.68% energy consumption savings over a 90.1 2007 baseline with process loads removed. And this is for EPAC. This is another design project that we have in the works. It is the Joint Base McGuire Dix Lakehurst Consolidated Dining Facility. In other words, this is our Fort Dix DFAC. This project is just over 30,000 square feet. This will have a geothermal well field, which is also designed to accommodate 100% of the building load. There will be 60 boreholes, each with a depth of 500 feet. Each borehole will have a spacing of 20 feet from one center of the borehole to the other center of the borehole. The system will be served entirely by ground source heat pumps with a makeup air unit, which also receives water from a water-to-water heat pump. The load side of the water to water heat pump comes from the geothermal well field, and the source side, the source side comes from the geothermal well field, and the load side comes from the building loop. We anticipate a 30% energy cost reduction over 90.1 2007 baseline, with a 40% energy consumption reduction over an ASHRAE 90.1 2007 baseline model with the process loads removed. This building is expected to achieve LEED Silver certification. This last slide lists the point of contact for the Ground Source Heat Pumps Renewable Energy Center of Expertise. At the top you will see myself, a co-chair, Dan Serkis, who is our other co-chair, Donna Johannes, who is our program manager, Jim Miller, who is our ERDC liaison, and Ben Barnes, who is also our ERDC liaison. If you have any questions about today's presentation, or you would like to engage our Renewable Energy Center, please feel free to give us an email. Thank you for your attention. Are there any questions?
Hope, I did have one question in the Q&A box from John at NAD. He asked, how much of the well field is underneath the parking lot? And he didn't specify which project, but are either of the well fields underneath the parking lots for these projects?
No, they are not. No, they are. We actually have quite a bit of real estate on both of these, and so in both cases, the well field is not located under the parking lot.
Here's another question from Linda at Fort Bragg. She asked, what is the average width of boreholes on the Fort Campbell project?
I believe it is 6 feet, but if she would like to see design drawings, I could certainly get those for her.
Okay, thank you. We also have another question from Franklin at HNC. His question is, what is the cost for doing design reviews?
Well, that is a good question. It varies if it's QC or QA review, and what the how much material there is to review. So, you know, if he has a particular project in mind, we would be happy to engage him and find out what level of review he would like conducted, and you know, if it's you know, an interim review or a final design review.
Okay, we have a question from Ralph. He's asking, can you share any life cycle cost data or what is the payback period for these projects?
The payback period for each project differs based on the region of their country that they're located in. If it is a, you know, full geothermal well field, if it is a hybrid system, what you know, what the building type is, it varies for each of it. What we can do, if he has a particular project in mind, however, is we could sit down and we can look at, you know, what the energy analysis would be, and then put some cost estimates together based off of design drawings or rough equipment sizing.
Okay. Do we have any other questions for Hope? Okay, I see one from Captain Houston. His question is, how did the soil type or quality at each location play into the designs?
Well, it plays into the design. A few of the things we look at is the soil diffusivity, the soil conductivity, and the undisturbed ground temperature. And before we complete our designs, what we will typically do is request that a test well be drilled. And that way we get to know what the soil conditions are before we finish our design. It also aids in sizing our well fields and knowing if there's you know, any ground considerations that we need to take into account, you know, loose soils, that type of thing. Are there any other questions?
David, we can barely hear you.
Okay, sorry, my apologies.
There you go.
Okay, here's another question from Captain Houston for you, Hope. Do some regions have better soils than others?
Some regions do, but you know, if there's a particular region that he's looking at, what I would suggest that he do is try to find, go on to, I think it's USGS, and try to find if they've done any test wells in there. He can engage someone from our center, and we can try to find test wells for that particular area or that particular installation. Test well reports.
Okay, thank you, Hope, for your presentation.
Thank you.
Looks like while we wait for Eric to get set up, we do have one more question regarding the first presentation. It's how much are you paying for testing and reports? I don't know if you have a generalized cost for that.
It varies per contractor and per region of the country.
Okay, again, if you have any other questions that you think of later on, feel free to email Hope. And if you'd like, you can see her slides. They're available down in the file share box in the bottom left-hand corner of the screen. Eric, are you ready to begin your presentation?
Yes, I am. Okay, this is Eric Mucklow. I work at headquarters. The Building Technology Program Manager. I work in the architecture section. I've been working on a lot of these energy-related things, and I'm the headquarters proponent for the CX, the RCX. I wanted to talk to you a little bit about geothermal or ground source heat pumps, especially kind of on a pulled back personal level. If you've ever wondered about converting your home to geothermal, I just went through that for half of my home, and I wanted to talk a little bit about the technology, so you have an understanding of what the difference is between the typical system and then what you can expect in embarking upon such a project, especially before 2016, which is when the 30% tax credit expires, which, as you'll see, will make a pretty large difference. Okay, well, first, the terminology, geothermal or ground source heat pump. Oops, it seems to have jumped over here. Okay, geothermal or ground source heat pump. We seem to have some crossed terminology in the industry, not so much on the commercial governmental side, but especially in the residential side. You still hear geothermal referred to a lot, and both are applicable. And if you think about the word, geo being earth and thermal of heat, thermal coming originally from the Romans, later adopted by the Greeks, talking about the warm springs, you can see that that's very applicable. But to clarify what it really is kind of leaning toward definition would be looking at what geothermal power plants are, where basically you're literally talking about warm springs producing temperatures in excess of 190 degrees Fahrenheit, which can then be used to drive a racine generator to create electricity. So you're really talking about hot springs like volcanic activity type of things for geothermal power. So I just want to make that distinction. Ground source heat pump as an alternative to air source heat pump is probably the more appropriate term to use, and that's what I'll be using the rest of my presentation. This is probably what most of you have in your house, is something along these lines, where basically you have an air handler somewhere in a mechanical room or basement, and then it's coupled by some copper piping to an outdoor unit that basically blows out a lot of air and makes a lot of noise. The inside unit is connected to ductwork that basically heats and cools your house, depending on what the thermostat says the demand is. So that's a very common arrangement, and that's basically the kind of context that we'll be talking about. Since this is just talking about converting one of these typical systems into geothermal, I'm not going to get into hydronic systems and all that other kind of things that are lesser used, but have more options today. Talking a little bit about how the heat pumps work so that we understand where these two kinds of heat pumps meet or intersect. I'm going to oversimplify the physics and just talk about Guy Lussick's law. Basically, he pointed out the difference and relationship between pressure of a gas and temperature. So each heat pump fundamentally has these components, as you see below. They essentially have the same thing on two different sides, one being a coil with a fan blowing across it, a couple of valves, same on each side, and then a compressor and a reversing valve. The reversing valve simply allows it to switch between cooling mode and heating mode. So we don't need to go too much into that. We'll just talk about the cycle of what's happening and how this thing heats and cools your house. So basically, the compressor runs and compresses the gas, which by the aforementioned law makes it heat up. So the gas heats up and goes through a coil which has a fan blowing across it to cause the air by conduction to pick up some of that heat energy of that hot gas. So the heat energy gets transferred to the air because the air is at a lower temperature and the gas is at a high temperature. So then that makes the air coming into your ductwork warm when you're in heating mode. So then the gas, as it does that, as heat energy is transferred into the air stream, the ductwork, the gas then continues on, and of course it's cooled down a bit to maybe call it a medium temperature, and then it goes back out to that outside unit where it goes through one of these fancy valves that basically releases that high pressure. And by the laws of conservation of energy and the pressure and volume law, we know that when you release pressure, it's going to cool down. If you've ever had an aerosol can, like one of those spray air dusters or whatever, and you sprayed it a while for a long blast, you can feel the can getting cold in your hand, and that's basically the same kind of thing. So the energy that was dissipated a moment ago through the air blowing across the inside coil is now being absorbed out of the air and coming into the back into the cycle again. So that's basically the fundamentals of how these heat pumps kind of work. You basically have a coil on each side, and they are literally transferring heat or pumping heat, hence the name, from one side to another. Cooling, of course, as a reminder, is simply the absence or removing of heat. And this is usually what these two major components look like. You have inside, you have the big box in your basement with the ductwork connected to it, and inside that box is fundamentally a coil with a fan and some other junk in there, and that has the copper pipes connected to that outside, which you can pretty well see from the shape of it is that big aluminum finned box or column that has the fan that pulls the air through that coil to either dump the heat or absorb the heat from the air. In a geothermal system, the inside unit is pretty much the same. It's got a coil in it, it's got the fan in it, but on the outside, instead of having a copper coil with a fan blowing through it, you have a circulation pump with a heat exchanger that's circulating water through a plastic coil. And that's buried in the ground, and this picture shows a horizontal loop installation, or slinky they call it. And this is a vertical situation where it's the same kind of thing. A coil is just long and skinny coil stuck down a tube into the ground several hundred feet. So the advantage, or the main difference is that the air source heat pump then cools or heats your house by heating or cooling the air outside. So basically whatever it's doing inside your house, it's doing the opposite to the air outside your house. If you're heating your house, you're cooling the outside. If you're cooling your house, you're heating the outside. The ground source heat pump is doing the same thing, but in the ground and not the air. And that's where the big difference in performance comes. Because the heat source, the air source, relies on getting heat from the air and transferring it into your house when it's seasonally cold outside. Basically in the winter when you're trying to heat your house, it's trying to get heat out of the cold air. And that's where the problem comes in, is because you get to a certain point where when the air gets below 40, as it gets harder and harder for that heat pool to pull heat out of the air. There's just not that much heat left in the air, and then what you have is like you have this ice frosting over on the coils. Of course, that's kind of also a defective system. And this is why usually, or actually all the time, air source heat pumps require a backup form of heat that gets used when the temperature drops below that point. Typically electric resistance heat in milder climates where it's not used that much, or where the heating costs are higher, they'd have like a separate gas furnace or something like that, gas or oil, to provide the heating that the air source heat pump can't provide. Geothermal, on the other hand, takes advantage of the earth. And as this map shows the earth temperatures throughout the nation, the earth temperatures vary very little compared to the air surface temperatures. In the diagram on the right, you see the horizontal arrows indicating the wide expanse of the temperature range. And going down the scale on the left-hand side is the depth. 0 is the surface level. The vertical dashed line represents the yearly average. This one says 50, so it's probably somewhere in the between the blue and the green in the map. So as you can see, if you just go down 18 feet, you're not getting a whole lot of fluctuation in the temperature below ground. And even if you're only at 4 feet, if you're doing a horizontal, or 6 feet, if you're doing a horizontal loop, you're only getting a plus or minus 10 degree swing rather than plus or minus 70 degrees or 80 degrees. So you're not, and most critically is you're staying above that 40 degree mark, or where it gets cooler or too hot for the air to be able to absorb heat that the air source heat pump is trying to dump into it during the hot weather. So this gets to my conversion. Basically, I have a house that was built in 1981, and then it had an addition added to it that was about the same size. So I had two separate 2.5 ton air source heat pumps. The original one had been replaced and is a little newer, but the addition one was in very sad shape. You can see in the pictures, and was grossly needing to be replaced. It would blow a couple fuses every year, and not to mention frost up if I didn't use the emergency heat, which would blow the fuses. So it had a lot of problems and needed to go. What I ended up doing was replacing it with a Series 7 water furnace, which is a variable speed. At the time, and I think still is, the only variable speed compressor on the market. Most of these things are dual speed scroll compressors. And that was coupled on the outside with two 300-foot vertical wells in a little parking area next to my house. And then if you can read the fine print up here, you can see the coefficient of performance, basically indicating that since you're pumping heat, you're moving heat instead of generating heat, you can actually get over a 3 or 4 to 1 ratio return on your electrical investment. So basically, for every 1 unit of electricity you use, you can get 4 units of heat back into your house. So these are some of the options I looked at. Basically, whether or not to go with a standard air source heat pump, replace basically like in kind of what was there. and maybe supplement it with a gas furnace, because I was getting killed on electrical bills. I had electrical bills during this snowmageddon of over $700 in a month. So that was something I wanted to get away from. Another option was a high efficiency inverter air source heat pump. Those use some technologies to leverage their performance so that they can perform well all the way down to like 15-degree air temperature. And it doesn't get below 15-degree air temperature that much here in the DC area. So that was a serious contender. And then the third option, of course, I was looking at was the geothermal heat source. And that was what I ended up selecting. And some of the main kickers is that this system was the highest in efficiency, and so the logic being that even though natural gas is very cheap right now, and in one of the software models it showed that it was competitive on a life cycle basis, except that I don't have gas service now. I'd have to get gas service, and that'd incur additional cost, both monthly and upfront. But if you don't use the energy, then if you you don't have to be subject to an increase in pricing as much if the cheap energy that you're relying on otherwise suddenly goes up in price. If some of us remember in the days before fracking and all that, natural gas had quite a big spike in cost, I guess about 8 years ago or so. So the geothermal turned out to be the lowest life cycle cost and the first cost after the tax incentive, about being equal, and we'll look at that later. Because the tax credit offset, as I mentioned, the cost difference. One thing I like about the geothermal is that I don't have that outdoor unit. Not only because the outdoor unit is subject to the extremes of weather and temperature and rain and all that, so it's got more of a maintenance concerns. But also, I don't like to hear the thing running or kicking on and off when I'm sitting on my deck out back. And actually, where mine was located, I have space for a little shed that I might explore now. So there were some other non-tangible benefits to going with the geothermal route as well. Looking at the costs, the air source with the natural gas, when I kind of looked at that and trying to run gas to my house and all, I realized if I did that just to buy gas for the geothermal system, I'd incur a lot of monthly fees and things that weren't factored into the equation in a modeling software that I ran, and so I didn't pursue that any further. I did get a quote for the high efficiency air source heat pump that came in for the one side of the house at another 2.5 ton system, being $18,800 for the replacement of that system. Now the System 7 that I mentioned, they don't have a 2.5 model. They have a 1.5, a 2, and then they go to a 3-ton model. So I had to basically round up and get a 3-ton model. And the quote for the inside unit, which included a $2,500 manufacturer rebate, was about $20,000. I got a couple of GWiz options that weren't really relevant to the to a comparison for the 18,000. But for a performance package for monitoring and a GWiz thermostat, that kind of thing. The main difference between the air source and the heat pump, air source and the ground source heat pump, is of course when you get into the drilling cost, the cost of that outside loop. Air source heat pump, of course, they just bring in that big aluminum coil with a fan on it in a box, and they stick it on the ground on a plastic slab, and they're done. Whereas the geothermal system is a lot more involved, because essentially you're building your own outside coil. So the total cost was $31,000. But when I get my tax credit next year, hopefully, that's the one risk, is that they change policies or something. Even though it's currently not set to expire until 2016, politics the way they are, I don't trust politicians. Let me just leave it at that. So you can see that the total cost then ended up being $21,765 versus an alternative of $18,800. And if you look at that in terms of the per ton difference, it's actually cheaper. Although you could argue that I didn't necessarily need the additional tonnage, but also the $21,000 included some other benefits that the variable speed model of the geothermal system had for humidity management. It has things where it runs the fan and compressor at a very low speed to prevent the air from drying out as much as the other typical on-off cycle of a dual speed or full speed system. So this is a software tool that is called Looplink. It's very expensive, but I downloaded a free 30-day trial version, and so I entered a bunch of the parameters for my site, trying to really figure out this stuff. More than you'll probably ever need to know. Your contractors will probably be using this software or a version of software created by the manufacturers. It's in water furnace and carrier's best interest to make sure that their customers have their loops designed properly, otherwise their systems end up taking the blame. So they have a lot of software tools that they provide to their dealers to be able to calculate these kinds of things. This assumed a couple of things that didn't make it an exact, accurate comparison. For one, the ground source heat pump, it was using coefficients of performance and energy efficiency ratings that were lower than my particular unit. As I said, most geothermal systems on the market were dual speed scroll compressors and not full variable speed, and Water Furnace with their System 7 has now come up with another level higher of performance. Of course, variable speed are things that, in the big industrial systems we've seen for a long time, but for the residential sector, this is something new. And also the one thing I suspect that, as I mentioned, the natural gas was the next on the life cycle cost basis. It calculated to be very close to being the same. In fact, it said a little bit cheaper. But then, since I don't have natural gas now, if you get a utility bill, you get billed for whatever the unit of the energy you're using, therms or whatever, natural gas. But then you also have all those other charges that get looped into the bill. And so on an annual basis, I'd be paying a lot of that extra cost as well, plus figuring out how to get natural gas to my house. So otherwise, you can see how these things fleshed out. Resistance heat basically has a COP of 1. It's simply converting electricity into heat, and it's creating heat rather than moving heat. And so all you're going to get is the amount of electricity you put in turned into heat. And then the ASHP here is the air source heat pump, which is the other, the typical scenario. Natural gas and, of course, propane. For those who are interested, this software also gave you a how many CO2 emissions that you would be saving with the ground source heat pump. If you're concerned about how much you're polluting the environment, this of course is not burning any fuel itself, but this is based on the region where I live. It selected the mix of coal-fired electrical production plants versus other natural gas and other things, so that it came up with this amount of carbon dioxide being generated in the production and distribution of the electricity to power the geothermal system. So even considering that coal puts out a whole lot more than CO2 than natural gas, it still ended up being less carbon emissions than a natural gas system. So some of the things to consider, looking at the difference, the alternative of just simply replacing like in kind with what I had, looking at the extra can of worms that I opened by going the geothermal route. For one, if you replace your existing systems, you don't have to worry about the health department. Anything that you dig into the ground, the health department is going to be concerned about, especially if it's a well. And not just for legacy reasons, but in the case of a geothermal system, they want to make sure that you're not going to have a conduit basically going from surface to the aquifer, where pesticides that people spray in your neighbor's lawn get or your lawn get soaked into the ground, and then they follow that well path all the way down to the drinking water supply. So that's why the geothermal wells have to be thoroughly grouted, basically, or filled in, not just for the thermal performance, which of course is an issue, but or something we need to have, but also for the health and welfare of the public. So therefore, you do have to go through the health department, which is a bit of a long process. My permit was processed fairly quickly, but nonetheless, it has like a $500 fee for them to come out and look, and then the other fees on top of that. So, and plus, then you're potentially going to have multiple contractors involved. You might be in an area where you have a one contractor does it all kind of thing, but from what I saw in my area, that didn't seem the case. Usually, there were drillers, and then there were mechanical contractors. My situation, I had the drillers come out and drill the holes, the drills, and they put the tubing down the holes, and the mechanical contractor came out and put the unit inside, and then a separate loop contractor that was another geothermal contractor, they were a subcontractor to the driller. They came in and tied the two together and flushed it and filled it and all that stuff. And you also have to coordinate the grouting of the wells with the Department of Health inspector observer. They literally want to see that grout happening. And since this will, no matter what they tell you, destroy your landscaping and your yard, you'll need some kind of a landscaping contractor, unless you're overzealous like myself and want to do it yourself, which in hindsight I probably should have just paid somebody. So another risk, of course, the policies with the tax incentives can change, among other things. So recommendations after lessons learned is to start the process early. You need to get that well permit moving, and to know that, you have to know where your loop is going to be and what type it's going to be. Identify both the possible as well as permissible layout options. By possible, I mean you might have a possibility physically of being able to run like a horizontal loop. Like I have a 700-foot driveway, and I could have run a horizontal loop down that driveway. In fact, a couple of years ago, I got a quote for doing that. But the problem is that goes through an easement, and so the county would not permit that being done. So even though it was possible physically, it wasn't permissible. So make sure you know what the requirements are from your state, and talk to them, and they'll help you out. Stay away from existing wells, because the process of the drilling creates a lot of vibrations and other below earth activity that you don't want to cause your existing well to be damaged or start sucking up muck or what have you. It's best to stay away from it. And I already mentioned staying away from easements. That's a requirement. At least in Fairfax County it is. You might need to check your locality. And make sure the equipment, and by that I mean the drill rigs, and you'll see in some pictures it's more than just a drill rig. They have a support vehicle and a lot of big filter bag they have to lay out and other things. That it takes some space to do these things. Discuss these options with your potential vendors. Have them come out to the site, look around. They can kind of give you a visual depiction of understanding of how they're going to get their drill rig into where you need it to go. In my situation, I looked at doing the other side of my house as well, but the big drill rig wouldn't be able to fit back there, so they on that side of the house, so they'd have to bring in a smaller tracked rig. But since that would be something that takes more manpower to operate and run slower, that the price would be another $1,000 per ton of cost to use that drill rig versus the big standard one. Stake the layout. The health department inspector, when they come out to do a pre-permit site inspection, they'll want to see the well staked out, include your extra locations. Always have some backup, so if they start drilling and they hit underground stream or spring or something, and it prevents them from drilling further, then in that spot, then you don't want to have to go back and have your permit modified and start all that stuff over again. So have some extra well locations already pegged out so that you can have a fallback plan without having to go back. You don't have to drill them all, as I've noted here. So just you do the ones that you need to do, and same with the depth. Tell the health department you're going to make it much deeper than you actually need to, so that if you end up, when they start drilling and they come up with shale and you thought you were on granite or something, shale having lower thermal performance, if they have to update the permit by saying they need to add some more depth, I mean, you don't want to have to go through that. Again, the health department's not going to make you dig it to 600 feet. If you said 600 feet, and even though you only need 300 feet, you can dig it to 300 feet and they'll be fine. Identify the scope with your contractors. Make sure they all understand who's doing what. Most of these contractors, they do a lot of the residential work, seem to have a kind of a common understanding about the mechanical contractor, what his responsibilities were. In my case, which I had the impression was common, was he installed the inside equipment as well as what they call the flow center, which is basically a heat exchanger and circulation pump mounted on the wall. And then the driller drigs the wells and then and grouts them with the health department, and then a loop subcontractor, which may be a part of the driller, connects the loop, runs the trenching and connects the loop back into your mechanical room through the wall in the basement or wherever that is. The loop subcontractor also has this cart thing that they hook up and they flush the tubing out to get any debris out and to get all the air out, as well as adding a 20% antifreeze solution. In my case, I had to come back and kind of do that twice, or do it in two steps, basically. And then after the loop contractor is done, the original mechanical contractor comes back out and does the final configuration and programming. Since this was a replacement of an existing system, we did it over the winter so that I could use the resistance heat backup. So once the mechanical contractor was able to get the inside system hooked up, we were then able to use it with the resistance heat while the loop was still being looped, being assembled. Because since in any retrofit installation, you need to figure out what am I going to do without air conditioning or without heat while they take the old machine out and before they get the new machine up and running. So I'd recommend, since the loop would not work, the air conditioning or the cooling mode would not work without the loop, but the resistance heat would, you might want to consider like a mild time of year when you're going into a cooler season or something, to have that accessibility. And my mechanical contractor, as a backup, also provided lent us some very large space heaters just in case something went wrong. So this is a picture of where I was going to have the wells put in. There's one stake over here that's one of the wells. The other well is over here somewhere. I went ahead and dug up and exposed some of the fiber optic lines because I was concerned. I knew that they had to cross it, so I wanted to make sure that they didn't cut it because they're right there at the surface. And excuse me, the blue line here is a culvert, which is storm pipe basically, which is open over here and open over here. So since that's exposed to the air and they're going to have to cross over it with the tubing or under, whichever the case may be, I think they went over it. And to make sure that they were going to insulate the tubing, the lateral at that point, since that was exposed to a cold air. Ground temperature around that pipe would presumably be colder. And so then the drill rig arrives. As you can see, it's quite a bit of a beast. There's the support vehicle over here. This is covered in snow now, but this is that parking area that we just looked at. Those blue lines are running through here, covered in snow now. And then away they went. And you can see the millings coming out of here. It does make quite a bit of a mess. They had a pipe going into a filter bag, which is over here in this top left picture, to basically keep all the millings from going down into the storm drains and clogging them up. That was going to be $500 for each one of these that they would use to fill and then take away, although they ended up only using one. This is the new unit, the water furnace system 7, return duct and the supply ducts. This is that flow center that I mentioned. So basically, the mechanical contractor installed this tubing, and then the loop contractor came in through the wall on the other side of the room, came across between these joists and came down and just tied in right here. They put in new electrical connections, separate ones for the unit and for the pump. And I thought that sticker was funny, burp me, which I think is referring, of course, to that cart to get the air out of the loops. This is our friendly neighborhood county inspector. He's actually from the adjacent county, being rented to my county. He came in and make sure that the wellhead was in the right place and that it wasn't in the easement and that everything was looking good. The 3 tubes you see here are the supply and return essentially for the coil, for the loop. And then this tube right here is one that they would put down with it for the grout filling process. They take that and then attach a fitting to it, which connects to a pump truck, which then pumps the grout. And as they pump the grout, filling up that hole that's 300 feet deep, they back out that tubing, as you can see them doing here. So they had the grout is a mixture of like a bentonite-based grout as well as a silica sand. It's enhanced for thermal conductivity. There are some people saying, oh, you don't really need all that. You can just do cement or whatever, because the ground around the well is not necessarily any, this high thermal conductivity. However, if you do move that gradation of the thermal transfer further away from the center point, then of course you get more essentially surface area that you're trying to absorb into. So here he is on top mixing just pouring in the silica sand and the grout into the truck. He had another assistant doing this also. They traded off. It wasn't the same guy doing everything. And so after he was done with that, the loop contractor came out and they dug their trenches, put the loops down. This is the loop of the plastic pipe, and you can't really see it there, but there's a T going down into the hole. They basically cut the top of that casing off and filled the rest of it in with the grout and did their little capping here with the supply and the return. So that's the one side going back around the house, and then this is the outside going into the basement. Of course, they sealed this up with hydraulic patching concrete. And here he is with the cart that would then burp the loop. So this is what was left on my parking spaces. And in the background there's the excavator they used to drill it, to do the trenching. And here you can see where I need a lot of work done on my grass. After they trenched and pulled all the dirt out and put it back, it's basically I need to put topsoil in and just totally redo my backyard. But I've had the system up and running pretty much at the very end of February. We were able to use it in ground source heat pump mode rather than just a resistance heat. And so my March electric bill was the first one that showed the results. And unfortunately, we had a unseasonably cold March. It was averaging the highs and lows. The average temperature for March 2013 here was 41.3 degrees Fahrenheit, whereas historically it's 45.1 degrees. Even so, I saved 20% on my electrical consumption in kilowatt hours. Now again, this is only a difference of the system for half of the house. The other half is still air source heat pump. Now, one thing I noticed is that the average temperatures for February were like 37 degrees or something like that. So if you average February, March together per month, it equated to 4,118 kilowatt hours per month, February plus March divided by 2 basically. But that got closer into the temperature range, so I saw that as a little more accurate predictor of the savings that I should be getting. And that would be 32% savings for just converting half of my house to geothermal. I've heard in sales literatures and other talks and things, people saying that, oh, you can save up to 70% on your power bills. I always thought that was a stretch because they don't know what else they're using power for, but this seems plausible, assuming that if I did the other half, I could have another 32% savings, be 64% right there. So,
Eric, I did get a
as that goes, are there any questions?
The first one from Todd, he asked, did the cost of the ground source heat pump include costs for a geothermal conductivity analysis?
No, basically I had a, that's very expensive. Usually you'd only do that on a big commercial project, because basically to do that right, you really bring a drill rig out and drill a whole well and then put a sensor down in it. So that really only makes sense if you're doing like a large array or a large project. But what I did have on hand is I had the original 1981 well record from when they drilled my water well. And so I knew that, at least on the other side of the house, that after 23 feet they hit, of mica and clay, they hit bedrock, which was shale. And then it was shale from there down to 270 feet. So I used that as an approximation for the Looplink software, and I basically gave an additional 5% safety factor and assumed a thermal conductivity of basically of shale, which of the rock is very good, but of the rock, shale is not so good. When they actually did the drilling, they ran into a band of sandstone, but that's since the alternative was shale anyway, that wouldn't affect my performance. In fact, I believe it would mean that I'd get a little better performance than predicted. But so basically, you can find out in your area. In fact, on the Fairfax County website, they have some geotechnical information, but you can find out basically from the geothermal contractors of other places they've done in your area of how far down they can expect to hit rock and what they use for thermal conductivity. I had a couple geothermal contractors come out, and only one of them said that I'd probably be expecting, just off the cuff, without doing any math, about 200 feet per ton. Others said 150 feet, and one suggested like 135, which to me looks like it was too little an amount. But then again, he hadn't run the math yet. 150 feet might have been plausible. The 200 feet was the worst case scenario, and so I'm happy with that. Again, at the loop, you're depending on the loop to be able to dissipate and absorb that heat, and so if it's undersized, you're going to compromise your whole system, especially in the peak load situations. So even though the drilling is one of the most expensive parts of it, you really shouldn't skip on that. The only thing that I wish that I had done, which I hadn't clarified with them, is that they went with 1.25" tubing, and so they didn't have what they call dog bones. Basically, as you have these, you have a 6-inch diameter hole, and you have a tube going down and a tube going up. Well, if those tubes twist together, then they have heat exchange going between the two of them rather than going through the soil. So they have these things that periodically they can snap between those two pipes, and they keep them spaced apart. That's most commonly used when they're doing 2 loops in one hole. So they have 4 plastic pipes going down, which means a little crowded, and that doesn't give you a complete doubling. It only gives you like 20% improvement. But since the drilling is so expensive, if that gets you over the edge of what you need, then that's doable. But I wish I had done the dog bones just because I like to be safer than safe. But anyway, well, I overwinded that answer.
Yeah, we had another. So try to run through real quick because I know we're at 4 o'clock now. Regarding permits, what?
Sorry.
Besides the health department permits, were there any other environmental permits, and how did you hear about your state and local requirements?
The state and local requirements, I went to the Virginia Department of Environmental Quality, but the Fairfax County website, they had a whole thing on what's required for geothermal and the different types of well. In Virginia, they have well regulations that classify wells as 1, 2, 3, 4, or 4. A geothermal well that's fully grouted is considered a class 4, which means that you don't have to have 50-foot setbacks from structures and all that you would have to have for a drinking water well. Drinking water wells have a lot of very tight requirements. There is one legacy requirement that they said that the well had to be steel cased from the surface to the bedrock. based on the drinking well regulation, but they would only require that of one of the geothermal wells, no matter how many wells you had. So I think that's just something they need to update the regulations, because once you fully grout it, then there's no need to have a casing, because you're not going to have contaminants getting into the hole because you've just filled it back in. So, but basically the process was, since I was replacing my mechanical system, the inside system was pretty much the same thing. No other building permit or anything was required for that.
No, like.
Otherwise, if you're doing, otherwise it'd be if you were doing a new system, you'd just have your standard mechanical and electrical permit, just like any other mechanical.
We had a number of questions regarding the lifespan of these well fields. Do you have an estimate for that, or are there other components of the system that might fail first?
Basically, the tubing itself is. I'm not sure if it's guaranteed or it's expected to last at least 50 years. That's one thing. They do have a technology they call direct exchange, where instead of using the high-density polyethylene piping, they use copper piping directly into the dirt at a very small diameter, and they run I call it Freon still, the refrigerant through it instead of going through the heat exchanger to water. The downside of that in my area is the soil is a little bit more acidic, and that can corrode the copper. And also there's a lot of stones and things that, if there's earth shifting or something, it could kink the copper. And plus copper right now on the market is extremely expensive. But otherwise, no, the well field itself, that's pretty much life of the building. But, of course, the pump is going to be something that's going to be probably replaced every 20 years. Now, comparing that to the air source system, the air source heat pump systems are a lot more exposed to elements in the fans. In fact, on my old system, I had to replace the fan motor twice, and I just bought the house in 2008. Otherwise, the mechanical system on the inside is pretty much the same as you'd expect in terms of durability as the inside of a regular air source heat pump.
Here's another question regarding the installation. About how long did it take to install one of the wells, and did you or your contractor have to coordinate the installation with your neighbors regarding noise, dust, or the movement of the heavy equipment on site?
I actually have a neighbor that shares my driveway, and so I did have to coordinate with him. And basically, we just made arrangements where we'd park at the end of an adjacent cul-de-sac instead of being able to get to our garages. But basically, I did have to coordinate with him just because of that. But otherwise, I didn't really do any extra coordination with my other neighbors to let them know what was going on. They basically drilled the holes in 2 days. It went pretty well, and a lot of what you see in that picture on a lot of that is mist going up into the air. A lot of millings are coming out, kind of piling up at the bottom, but because the water is coming up out of the ground at 56 degrees, it was very cold that day, and that's just the steam. It's not like it's going to be dust covering everybody. There was a lot of dust piled up, somewhat granular dust millings, on the ground, but not to the extent that it invaded the neighbor's yard. Now, if you were someplace where you had a neighbor like right next door, then of course I'd coordinate with them just to make sure, because they probably would get some kind of impact. But this was done during the work day and when these people are at work anyway.
Yeah, we had a couple of questions about multi-use of the wells themselves. First is, could you retrofit an existing water well to add a fourth pipe in there or I guess a couple extra pipes in there for your supply and return, so you could turn to a geothermal well? And then the other one was could you add another pipe into the geothermal well to kind of pre-treat your hot water to reduce the electrical load?
Yes. Yes, basically, on this side of the house, I already had a heat pump water heater in my garage, which in the summer cools my garage. But basically, that's a standard option there is such a thing. Basically, the geothermal systems have the ability to, when they're in cooling mode, to take some of that heat that they're dumping in the ground and instead use it to heat your hot water. So that's, in my case, my hot water heater, I already had a new heat pump one, and it wasn't co-located with my mechanical system. So on the other side of the house, I think I probably will do that, but that's very commonly done. Although you only get the benefits to that when you're in cooling mode. In heating mode, they have it so that you can still use the geothermal system to heat your hot water, because you're still heating your hot water with a 4-to-1 ratio of your energy rather than using strictly resistance heat. So that is an option that you can get on the system. So it's not an extra pipe that goes in the well. It's just the mechanical unit inside has that capability. They just add another module for an extra set of pipes going in and out of it. And what was the other question about? Oh, the drinking well. Well, yes, there is something. Google standing column well for use on converting a drinking water well, an old well, into a geothermal well. That is done. Basically, they did not recommend or said you couldn't do it if you're still using that well for drinking water. That was an option we discussed on the other side of my house where my drinking water is. If I hook up to city water, which is now in the area, I could convert my old drinking water well into a standing column well. But because basically the way that works is you dump the water on the top and pull it out of the bottom, or vice versa. Using the whole casing of the well as or the whole hole as a heat exchanger, or if you do a closed loop system, you can do that as well. But I think that would not be a standing column; that would be just one well. So you wouldn't have the same heat dissipation ability, because the open loop aspect might be something your local county might prohibit. But since that would be circulating well and all that, it's stirring up all kinds of crud and stuff in there. You wouldn't want to drink that water, especially because you don't want to turn on a tap and have 95-degree water coming out at you when it's the cooling season and all that. So anyway,
yeah,
Google
the final
standing column well if you have
before
an
we
existing
close
well
out
that you
is
want to convert.
given just the limited
that is
data
an
that you
option.
have from March. Have you calculated a
more
payback,
questions of
a
note?
return period for your investment?
Basically, the software did that, but the way I was looking at it on my original price breakdown, the difference in cost was only a couple $1,000s, and I think that's going to be only like 2 years that I'd be able to recover that. Let's see, where is that slide? Yeah, the difference between the 18.8 and the actual the final cost. Let's see, 21,000 minus the 1595 for the options that weren't really a comparison. You're at basically 20,200. You're only a couple $1,000s off, and so if I figure 32% of my power bills, which in the winter are usually like $600, and then in the summer go up to $300, and then spring and fall about $150. That would pay for itself in a couple of years. And that would be assuming that electrical rates and all that don't go up any more than the prediction of the software. But so yeah, I'm thinking that it'll pay for itself compared to these two options. Now, what I did not do is look at the option of just using a very cheap air source heat pump and paying, $700 power bills for the rest of my life. I just couldn't live with that. I do think that energy costs are going to continue to climb, especially once. Right now we're experiencing very low natural gas prices, historically low natural gas prices, as all these coal plants are being shut down and natural gas plants are replacing them. Whether that's deliberate or not, the basic laws of supply and demand are going to kick in. with that much increase in demand, and the prices will go up. So I think that right now the attractiveness of natural gas may not be something that would last the full term of the investment. Right now, really, what breaks it, I considered basically the equipment to be about the same in cost, and because again, this is a larger piece of equipment. So if you had a 3-ton already instead of a 2.5-ton, you might be looking at the same cost. But the difference really was the drilling in the loop. And as you can see, the tax credit almost paid for that. I mean, basically, really the difference there was $200. You could argue I just got that already with March.
Oh, that's not a problem.
Okay, so you said that was the last question. It's 4:12. I guess it took you a little bit over. I apologize for that. My email address. Oh, sure. There's my email address. I'm also in the global. If anybody has any other questions.
On the website,
and I believe we have this recorded, and we'll have this posted on the website as well.
The recording should be available this Friday on the YouTube channel, and there's a link to the YouTube channel from the Sustainability and Energy website. If you did have any other questions that we weren't able to get to, please email either myself or Eric, and we'll be happy to answer those. Thank you, Eric, for your presentation, and we'll go ahead and close out this meeting. We'll have our next webinar next Tuesday at 3 o'clock Eastern Time, and you'll get an email reminder with the topic for next week. Thank you all for joining us, and have a good afternoon.